Yep, and then you can start.
Hello, everybody. It's my great pleasure to present to you our next speaker, Dr. Paul Jaffe, a colleague at NRL and a wonderful person. He's an electronics engineer at NRL DC, and in the past 25 years, Paul has worked on more than 24 space missions, often as the lead scientific investigator. He's been the editor for 2 NRL-led space solar power study reports published in 2009 and in 2019, and they're widely distributed. His research interests include power beaming, space systems, renewable energy, and K-12 STEM education. Paul has authored and co-authored numerous technical publications and made numerous appearances on television, in radio, in print, online media, referencing space solar power and power beaming. He's also been a TED Talk speaker. And among his numerous awards, I'll mention one. Back in 2016, Paul led a team at NRL to win most of the awards from a Pentagon-sponsored Innovation Summit, focusing on power beaming. His work won the Innovation Award, the Presentation Award, the Collaboration Award, and the People's Choice Award. He kind of swept the entire competition based on his pitch for power beaming from space. And I think you'll find him an excellent speaker today. Thanks a lot.
Chris, thank you for the kind and flattering introduction. It is my immense honor and pleasure to be here to speak to you, and I'm extremely grateful to the conference organizers, Chris, Jen, JC, and everyone who's put so much time and effort into making this conference happen. So I'm going to talk to you today here at Wireless Power Week about wireless power and about the subset of wireless power that I believe we should all call power beaming. And I will, during the course of my pitch to you to use this nomenclature, talk a little bit about what's happened recently, not just at NRL, but elsewhere, and sort of the context for making this differentiation in terminology. So we'll start by just doing a quick review of some of the things that have happened recently at NRL. Back in 2019, we did at the Naval Surface Warfare Center, Carter Rock in Bethesda, Maryland, a laser power beaming demonstration in which over 400 watts of power was sent over a distance of 325 meters. And this is particularly notable because there was an integrated safety system that allowed the 100+ attendees for this demonstration, which spanned multiple days, to witness the demonstration without having to use any laser safety eyewear. And this was done by creating a virtual enclosure around the beam. One thing that's come up already several times during the course of this conference is the discussions of safety, and particularly of power density, and the importance of ensuring that only safe power densities are accessible to users and the general public. And this was a main focus of this particular demonstration. Last year on the International Space Station, NRL was also behind a STEM demonstration conducted by astronaut Jessica Meir, pictured here, where we sent a very simple power receiving element consisting solely of an LED and a Schottky diode, which she used to demonstrate wireless power on the International Space Station using the space station's Wi-Fi as the transmitter source. And this receiver is so simple that it doesn't require any soldering skills. You can actually just twist the parts together and it will work. And this is something that K-12 students throughout the country now have been able to successfully replicate at home, even during the pandemic, just by getting inexpensive parts and doing it at home with their own Wi-Fi routers, or you can even use a smartphone to do the same demonstration. For each of these, there's a video on the NRL YouTube channel if you'd like to learn more. And then finally, on the right side, just about a year ago, we launched on the X-37B spaceplane the first prototype for solar power satellite power conversion into space, into orbit, that has been done to date. And this converts sunlight into microwave energy. It does not actually radiate from the spacecraft for a variety of reasons, but this is the first test in space of hardware especially for solar power satellites. And we'll have a paper coming out later this year with the results from that. It is still operating successfully and sending us tons of data from orbit. So something to stay tuned for. And then finally, it's not on this chart, but also on the NRL YouTube channel is an additional power beaming demonstration that was conducted in January of this year in Seattle, Washington, that is a successor to the first one I spoke about, the laser power beaming demonstration. So another thing you can find on NRL's YouTube channel or in our press releases. So just a little bit about NRL. So let me start by defining power beaming. So we know wireless power is sending energy without using wires, and that can be done in a variety of ways and in a variety of circumstances. We'll define power beaming as the delivery of meaningful amounts of energy across long spans of free space without moving mass and, of course, without using wires. So long, of course, is a relative term, and I'll delve into that a little bit more farther in my talk. But the scenario usually looks something like this. You have a location that is difficult for some reason to get energy to, whether it's a drone in flight or a remote sensor or something similar. And there always exists a place where it is easier to get energy, whether it's the grid or a power plant or a battery or a generator. And oftentimes there is not a feasible way to connect these two places, whether by wire or by fuel delivery or by anything else. So this is where we enter power beaming, this ability to get energy over a long span of free space when a physical connection is not possible for whatever reason. Now, here's a slightly more detailed look at what such a link would look like if we break some of the blocks on the previous chart into their components. There's power conversion that occurs both at the transmit side and at the receive side. And there's typically some sort of transmitting and receiving structure or aperture, if you like. And the blue boxes that you'll see here are 15 different parameters that are of interest for implementers and for adopters of this technology in different applications. So they include some of the usual suspects like the input power and the output power from which you could calculate the link efficiency. It also includes the size of the apertures, the accessible power density, the peak power density, the distance between the transmitter and the receiver, the mass and volume of each of these subsystems, all of which are important for implementers of these kinds of systems. Now, there are a number of different places in the spectrum that we can do power beaming. Most of this conference focuses on microwave and to a lesser extent on millimeter wave. But as you saw on a previous chart, it can also be done with lasers using tuned bandgap photovoltaics. And the reason for the selection of these two regions is because most of the stuff we do today is still on Earth, and we have the atmosphere, which is a great thing to have, gives us oxygen so we can breathe, but it does attenuate some of the electromagnetic energy that travels through it. We do have these nice windows in the microwave region as depicted on the right side, as well as in the optical and IR regions. So that is where the focus of power beaming and the selection of modalities arises from. Here are a few examples where laser power beaming has been demonstrated in the past. This is far from exhaustive. There are quite a lot more, but this is just kind of a representative sampling. Almost 20 years ago in Europe, EADS Astrium demonstrated laser power beaming to a simulated planetary rover that then traversed a simulated planetary terrain. In the upper right, you can see a quadcopter that was powered in 2007 by a team in Japan at Kinki University. This quadcopter actually has on it a small camera, and in the disaster scene that's depicted there at the bottom of the picture, there's a victim, and they showed how they could locate the victim with the camera by powering this drone continuously. So instead of having to go back to swap out the battery or to replace it with another drone, it could fly effectively continuously just on the laser. And this same concept has been demonstrated now on numerous occasions. On the lower left is an interesting demonstration that occurred at the University of Maryland in 2012, and it was documented on the British television program Bang Goes the Theory, which you can watch online if you elect. And the notable feature of this demonstration, which occurred over about 1/4 of a kilometer, is that it was conducted at about 1.5 microns, which is a optical wavelength, which is much safer for your eyes than, say, 1 micron. So as part of the demonstration, the host of the television program actually stuck his head into the power beam to show that he could do that without risking harm to his eyes or his skin. And admittedly, the power at the receiver is only on the order of 10 watts, but that's still pretty good for demonstrating the safety of power beaming. And then finally, the 2 other pictures at the bottom there are associated with demonstrations that were conducted with the participation of power light technologies, formerly known as laser motive. One was laser power beaming to a fixed wing aircraft, a Lockheed Martin Stalker vehicle. The red spot you see on the receiver there is not the laser, but rather a beacon for the laser, which was in the infrared to track. And then the final picture was a demonstration that was done prior to the one that I spoke about earlier that was done at Carter Rock. There's of course been plenty of power beaming activity in the microwave region as well. Going back to 1975, a sort of golden year for power beaming with the efforts of Dick Dickinson and William C. Brown. In Waltham, Massachusetts, they did over about 1.7 meters, what remains to this day the most efficient instance of power beaming that has yet been demonstrated. 54% from DC in to DC out, all losses accounted for. And that same year, they also conducted what remains the longest distance, highest power microwave power beaming demonstration conducted at the NASA Deep Space Network node at Goldstone, California, where that large dish in the foreground sent energy to the receiver on the ridgeline, which you may be able to make out has this white area that has a little notch in it. Below the ridgeline is a array of lights that reflects the power density falling on the receiver. And they actually recovered 34 kilowatts of the power that was transmitted. And the power that actually fell on the receiver was converted with an efficiency of in excess of 80%. Now, of course, a lot went past it, but it's still pretty admirable conversion efficiency for the mid-1970s. And there's been tons of work done in Japan, including Milax powering this fixed wing UAV above this vehicle that's beaming power to it, charging a phone from this lighter than aircraft. And then this is just one of several recent sophisticated microwave power beaming demonstrations done in Japan, many of which are associated with Kyoto University and Professor Naoki Shinohara, who you may have seen in the WPT school and elsewhere. So if we take these demonstrations and we put them all on a log-log plot, as I've done here, we have logarithmic distance on X and logarithmic power on Y, you can get a sense of the landscape of what's been done for those metrics that we really care about, the distance and power. And you'll see the Goldstone one in the upper right there. And here is the high efficiency one, the only demo to be greater than 50% end-to-end efficient. And then also notable are the ones in which the safe accessible power density was controlled so that it would not pose a hazard to animals or people in the area. So and those include the power transmit over laser demo I spoke about earlier, the one at the University of Maryland, and then the consumer products from the Israeli company Y-Charge, which has also participated in previous wireless power transfer conferences and wireless power weeks. So you may be familiar with them as well. Now, if we take that set of demonstrations and kind of extend the axes a bit, we can see that there's been a lot of proposed power beaming links over much greater distances with much greater powers that we have yet to achieve. And a number of these are for solar power satellite systems, the idea of collecting the abundant sunlight in space and sending it to the ground wherever it might be needed. You can think of it in the same way that you might think of how GPS revolutionized navigation. Solar power satellites might do the same thing for energy, but there's certainly quite a few unknowns yet to be resolved. So we can look sort of at the same plot from a functional standpoint, and this is a chart that I'm using with permission from PowerLight, so it necessarily focuses a little bit more on the laser power, but you can see at the lower distance, lower power levels, shorter distances, consumer devices, industrial devices, and then increasing in power and distance all the way up to solar power satellites with many applications in between. We can look at this in a slightly different way. You may be familiar with R.C. Hansen's microwave scanning antennas, a sort of classic book that deals some with aperture theory and arrays. And by looking at the relationship between the distance and the diameter of the transmit aperture and the diameter of the transmit aperture and the operating wavelength, you can see where the reactive near field, the radiative near field, if it exists, and the far field all come into existence given certain assumptions about the transmit aperture. From a practical standpoint, you can think of each of these regions roughly as where the reactive near field is where we have inductive and capacitive wireless power, the radiative near field is where we have power beaming, and then once we get to the far field, it's more of an energy harvesting instance. So one way to break this down, a little bit less accessible to the layperson, so we could also come up with an arbitrary human scale definition of power beaming. History traditionally has used human scale as a reference for many different units of measurement. So I'm going to propose here sort of three relatively simple, understandable parameters that we can apply to power beaming to distinguish it as a subset of wireless power. So the first, again, somewhat arbitrary, is just demonstrating an end-to-end efficiency of at least 1%. If you start to get lower than that, it's kind of like, well, why do you bother? It's more like a communications link maybe than a power link. Similarly, for power beaming specifically, we want the distance to be probably at least a meter, right? So like if we're getting closer than that, it's probably more suitable for the inductive or capacitive resonance that we are much more familiar with. So we'll arbitrarily say a meter, again, kind of a human scale, and we'll add the caveat that this should be beyond the reactive near field of the transmitter. And then finally, we should meet those first two conditions for at least a minute. So we're not just talking about like a pulse or an impulse of energy, but actually doing this on a sort of continuous basis, or at least having the ability to. So taken together, you can think of these as the 1-1-1 criteria, 1%, 1 meter, 1 minute, as a way to say whether something qualifies as power beaming or not. So this is going to eliminate a lot of things that look similar, but are not, like communications links, where you're really just trying to make sure that the signal is above the noise. This different from directed energy, where you're not really trying to recover the energy at the receiving end, but rather to cause some sort of disruption. It's distinct from energy harvesting, where the transmitter might send energy in lots of different directions, and it's going to be difficult to achieve that 1% end-to-end efficiency. And while we might use hardware from radars to do power beaming demonstrations, the goal for those is also different, and generally the energy is not received and captured at the end. And then there's the whole gamut of applications covered under the industrial, scientific, and medical bands, the ISM bands, including microwave ovens, industrial processing equipment, and medical devices, and also eliminating systems that do operate within that reactive near field, the instances of capacitive and inductive resonance. So we can look at this, if I take the things from the previous chart and sort of depict them on a plot here with increasing power density on the x-axis and increasing distance limit on the y-axis, you can see sort of where they fall. And this shows you where power beaming is a subset of wireless power transmission. And I'm not sure why my label for wireless power transmission in that large box in the center is missing, but power beaming is a subset within that. You can see there is some overlap with energy harvesting, because you can, of course, augment energy harvesting by putting more power into a given area or a receiver. And you can see where the other applications of electromagnetic waves fall. And I think it's important to recognize that power beaming doesn't necessarily need to be done on the electromagnetic spectrum. There's plenty of researchers that are working on using acoustics for power beaming, certainly you can do that in places where you are going through a solid medium rather than through free space. And there's a number of other means that you could use as well. But this is what you might use to compare when electromagnetic waves are the choice for sending the energy. There's wireless power transmission. Okay, so I'm gonna sum it up here and I'll invite your questions. I'll say first that there's kind of broad consensus across the scientific world that nomenclature matters. Like if you call something a giraffe and I call it a penguin, there's going to be problems. And it's important for there to be common language that is clear and unambiguous. It's also important to note that language evolves over time, right? So we've been using wireless power as the designator for this technology since the 60s, but things are changing, right? Like there's no Qi in the 60s and 70s. There are no widespread EVs in those times. As an example, like if I had told you the word phone in 2000 or 1990 or 1980, you would almost certainly think of a landline. But if I tell you that today, you would think the same word refers to a smartphone. So these things evolve over time. And I think that there is value for our community to use the terminology power beaming when we are talking about this particular subset of wireless power, where it is over longer distances, where it is not a charging pad per se, just to avoid confusion. So I will leave it there. I'm grateful for your attention and I welcome any questions that you might have. Thank you for listening.
So we don't have any open questions yet. Perhaps we can start this off with a few questions for Paul. Paul, what are the greatest challenges right now to the widespread adoption of power beaming? And who's going to get there first, lasers or microwaves?
Oh, great question, Chris. So I wish I knew the answers to those. I'll take a stab at it. So certainly one of the biggest obstacles is frankly just awareness. Like there's a lot of people who I talk to and they've never heard of this, right? The idea that you can send energy through the air is completely foreign to them. And this is despite the fact that they use on a daily basis communication technologies that do exactly that, right? But the idea that it can be used for meaningful power transfer is still not at the front of most people's awareness. And this even counts like when a lot of them use Qi or they charge their phone wirelessly or they're familiar with this. But the idea that you can do it over longer distances is unfamiliar. So the question of laser versus microwave, I think really depends a lot on the application context. So each of them has strengths. Microwave, particularly at the lower end of the frequency band, is fantastic at going through the atmosphere and for dealing with adverse weather, whereas that is a real challenge for laser. On the other hand, laser and optical power transmission, because the wavelength is so much shorter, allows you to have much, much smaller transmit and receive apertures versus microwave to achieve the same beam collection efficiency. So they each have strengths. And I think that the application is really going to drive like where success is going to happen first, right? So I guess one possible application area is for drones, right? Like drones do a lot of great things for us, but if they're electric, they have limited battery life, and there's a cost associated with bringing them down, change the batteries, or having like a rotating series of drones to like provide continuous coverage. So the idea that you could have a drone, power it wirelessly while it's in the air, do effectively in-air refueling, allowing it to stay on station indefinitely, has a tremendous amount of value in many applications. And we're starting to see the users for that really have an interest in power beaming. So as has been mentioned by some of the other keynotes and other presenters in this conference so far, there is a really big challenge on the regulatory side. For microwave in particular, there's no free open spectrum. There's no vast swath of spectrum that's just waiting to be filled by power beaming. So there's a significant challenge there. There has been progress made both on the consumer side and certainly in venues like the ITU, especially by the Japanese under Shinohara Sensei's leadership. So I think that's a pretty significant challenge. And there are still plenty of component technology challenges that remain to be addressed to increase the efficiency, to reduce the mass, to deal with the thermal impacts of the transmitters and receivers, and to just integrate them in ways that are really conducive to some of these nearer term applications.
We have a question from the audience. What is the next big upcoming demonstration to watch out for? There are several, correct, Paul?
There are, yeah. So hopefully by the end of this fiscal or end of this calendar year, we should be seeing some pretty remarkable demonstrations coming out. I can't say too much about them now. I know there's a bunch that are slated for the US. There's a bunch slated for around the world. So this is a really exciting time for power beaming, because I don't think really since the 70s have we seen kind of the level of activity and renaissance that is occurring now. And while it may yet be a while before we do surpass the efficiency, distance, and power level records of the 1970s, we're definitely getting close. And I think that a lot of the demonstrations we're going to see will show more clearly the path towards practical implementations, right? So a lot is made, I think, rightfully about the Goldstone demonstration, which used this huge, I think, 26-meter diameter aperture to accomplish this high power, high distance demonstration. And that's just not practical for a lot of things that we want to do. Like, no one's going to put that on their house or at their forward military base. So I think a lot of the demos you're going to see in the upcoming 6 months or so will show that we are getting closer to a practical implementation, even if we're not surpassing the absolute power and distance records.
Could you comment on the economics of power beaming? I know this is something you've thought a lot about.
Indeed, yeah. And I have to give a shout out to Dick Dickinson, who wrote an excellent paper for the International Astronautical Congress about this, I think back in 2003. But at the end of the day, many of the applications are going to be driven by economics. So you can kind of win on cost or on features, right? Now, power beaming definitely offers features that you can't get any other way, and there may be some users that are willing to pay the added cost to unlock those features. And then you also have to look at like what the alternatives are, right? So one of the reasons that the US Department of Defense has been interested in this is because moving energy around is taxing and dangerous, right? It is expensive. It puts people and equipment at risk. Many lives have been lost delivering energy around the world. And the idea that you could deliver energy wirelessly between 2 points or even from space to an arbitrary location on Earth without having to have fuel convoys and risk and people driving trucks or flying helicopters is super attractive. But it still is constrained by economics, right? Like, no one is going to do that if it costs 1 billion times more than the alternative. So part of the maturation we're seeing in these different technologies has to address elements that are ultimately going to be related and contingent upon the costs.
I'd like to ask other people in the audience, please ask your questions if you have any. This is your last chance. Okay. Well, thank you very much, Paul, for this excellent talk. We appreciate it.
Again, I'm grateful for the opportunity, and especially to the conference organizers for making this event happen. So thank you very much.
Yeah. Thank you very much, Paul and Chris. Yeah, we should start in 2 minutes the technical session, far field wireless power transfer. So we'll take some break. 2 minutes or 1 minute now. Yeah.
We should also thank Paul for that talk. Thank you very much for addressing the conference today.
Mohammed, this is JC. Maybe
Yes.
you can bring up the PowerPoint.
Sure. Yeah.
The PDF. I'm sorry.
Sure. Sure. Yeah. Yeah. Can you see my screen?
Yes, but it's not in the presentation mode.
Sure. Sure.
For
Yeah.
PDF.
Okay.
Great.
Yeah. Thanks, JC. Okay. So thank you very much all for attending today. We should be, it's my pleasure to host this technical session, TS6, Far Field Wireless Power Transfer. I am the chair of the session, Mohammed Abu Zaid from San Diego, USA. And also Chris Rodenbeck from US Naval Research Laboratory, Washington, DC, USA, is co-hosting this session with me. Would like to thank him for that. And so today we should be going through our speakers. We have 11 speakers, and they should be presenting their work in kind of 2 to 3 minutes. And I should be presenting here or sharing here the 2-slide presentation for each presentation. And after we go through the presentations from our speakers, we will go through a Q&A session, which will be 30 minutes. And I'd like also to thank our speakers for taking the time today to present their work. And with that, we will start by the first presentation, which is from Enrico Fazzini about range selective power focusing with time controlled by dimensional frequency diverse array. Yeah, so Enrico, can you go on?
Yes, can you hear me? Everyone, can you hear me?
Yes, we can hear you. Go on.
Okay, thank you. So welcome to everyone. My name is Enrico Fazzini, and we present our work presented by Mohammed. So as we can observe in the left top part of this slide, the goals of this work was exploiting the frequency diversity for wireless power transfer purposes. For frequency diversity, we intend the technique for which we use radiating elements for which each radiate elements radiate a frequency that is slightly different from the frequency frequency of the signal radiated by the neighbors. And so we want to investigate on the 3D properties of this frequency diverse array system and overcome the limit of the FDAs that until now we know in literature. So at this aim, we introduce our radiating structure that is called a bidimensional array with monodimensional frequency diversity. This is a planar array for which we have an application of 8 different frequency along the column, we can say a vector that we can see in the structure. So as a result, as we can observe on the top right of the slide, we have a counterbalance the displacement in time that is typical of the frequency diverse array system with the new concept that we call the time-controlled frequency diverse array. That is a time-based technique strategy that we introduce in order to counterbalance this displacement in time. And after this, we have improved the focusing capabilities of the frequency diverse array, introducing the frequency diverse array with the logarithmic element distribution. So we pass from the typical S shape in frequency diverse array system to the more focused and precise beam in which we can concentrate the energy. The method that we used in order to examine this system are the simulations and the experiments, and simulation made with approximately with MATLAB, and experiment performed using not the array presented in figure, but a subsystem composed by 4-element array and operating at 1.8 gigahertz range. Finally, as we can see on the bottom right of the slide, the conclusion can be drawn, and so we can state that through our analysis, the standard frequency diverse array system can be used for radar application, in particular localization application of the target that of course we want to energize, and our new concept introduced as the time controlled frequency diverse array can be used for water power transfer application, for example for UAV or battery-less wireless sensor networks application. Thank you for the attention.
Thank you, Enrico, very much for your time. Our next presenter will be Romia. Will be Moro.
Yeah.
Yes, Romia Moro. So can you go on?
Yes, thank you for introducing. I'm Ryoma Moro from University of Tsukuba in Japan. Today, I'd like to talk about the microwave power transfer to a drone. Yes. First of all, this study aims to demonstrate 28 gigahertz microwave power transmission to a free flight small drone in microwave anechoic chamber. In order to achieve it, we introduced two technologies. First one is power beaming technique that scaled transmission power to a drone. In our experiment, power beaming was performed only for single axis. Secondly, the drone was autonomously controlled. The drone was programmed that hovers over the transmitter antennas at a height of 80 centimeters. In our experiment, transmitted power was 3.9 watts. As a result of a free flight experiment, rectangles attached underneath of the drone continuously receive DC power about 20 seconds. As you can see, top of left. So we successfully demonstrate free flight experiment with 28 gigahertz microwave power. The equation we derived could roughly estimate efficiency from the state of the drone. To improve efficiency, we concluded that more accurate control for a drone is necessary, such as using 28 gigahertz microwave power. In addition, a diode with better conversion efficiency in the operating region is desirable. That's it. Thank you.
Thanks, Romia. Our next presenter, Takanori Washiro. Can you go on?
Yes, thank you for introducing me. Can you hear me?
Yes.
Yes. Today, my name is Takanori Washiro from NTT, Tokyo, Japan. Today, I'd like to introduce our electric field resonant antenna for wireless power transfer. And please, next slide. Okay. Our motivation is developing the antenna of the high efficiency and has a wide alignment tolerance of the antenna. In order to realize this, we develop a new kind of antenna, and the antenna structure is based on the infinitesimal dipole. There are two electrodes in our antenna, and they are connected by the resonant antenna, resonant coil. And it works as an infinitesimal dipole, and there are two kinds of electric field around the dipole. One is ER. This is a longitudinal electric wave, and another one is E theta. This is a transverse wave. And we develop two kinds of antenna. One is E theta antenna, and another one is ER antenna, and measured the the characteristics of the both antennas. And since the ER is the longitudinal wave, so we find out the ER antenna has no polarization and have omnidirectional characteristics, and which shows a very high transmission efficiency as well. And finally, we measure the attenuation slope of the antennas depend on the antenna distance. And we find out that the transmission efficiency is inversely proportional to the distance of the 6th power of the distance. And it is really consistent with the theoretical expectations. So conclusion, we developed the electric field resonant antenna based on the infinitesimal dipole. And it shows many advantages for wireless power transfer. Particularly, the ER longitudinal electric field has a very wide alignment tolerance of the antenna. So we believe that it is very useful to use the wireless power transfer technology in various kind of applications. Thank you.
Thanks, Takanori. Our next presenter will be Mingyu Liu.
Yes. Well, thank you. Could we go to the next slide? The topic of this piece of research is retroreflective beamforming. We have been working on retroreflective beamforming for quite a few years. The basic concept of retroreflective beamforming is that microwave power beams are guided by Pylar signals. So on the top left here, we used a warehouse as an example. Suppose there are electronic devices in the warehouse that are in need of wireless power. They need to broadcast Pylar signals first, illustrated by the blue color in the graph. And the wireless power transmitter is installed over the ceiling or on the walls. So it includes many charging panels, and each charging panel is further composed of antenna arrays. So the wireless power transmitter will receive the Pylar signals and analyze the Pylar signals. And in reaction to the Pylar signals, the charging panels generate beam the power, wireless power beams toward the locations from which the devices, from which the Pylar signals are broadcasted. So the beauty of retroreflective beamforming is that the microwave power beams always follow the locations of the mobile electronic devices. If we assume that the wireless power receivers are mobile, or if we assume that their locations are unknown, then the wireless power beams always follow the locations of the wireless power receivers as long as they generate Pylar signals periodically. And we have been, during the past few years, we have been working on one wireless power receiver scenario. So but only recently did we start investigating multiple targets. So in this presentation, I call them targets. The targets refer to wireless power receivers. When there are multiple targets, actually, we found quite a few interesting issues which were not studied before, in our opinions. So on top right, actually, we articulated some of our findings. And because I only have 2 minutes, it's not very easy to explain them thoroughly. But basically, if there are multiple targets and if they broadcast Pylar signals simultaneously, we found that it is very necessary to tell them apart, to tell apart the Pylar signals from multiple targets. And if they are not differentiated from each other, seemingly it still works. still multiple power beams would be generated, but there are a range of technical issues. So basically it is our major conclusion. If there are multiple targets, and if they broadcast pilot signals simultaneously, it is very necessary to tell them apart. And we think there's a pretty interesting analogy. So the analogy is the wireless communication to multiple targets. So if we want to communicate with multiple targets, and there are many techniques to differentiate them, including TDMA, FDMA, CDMA, SDMA. So here, if we want to generate multiple power beams to multiple targets, respectively, it's very similar to SDMA, space division multiple access. But in wireless power, it seems that on top of SDMA, we must enforce another type of DMAs, either TDMA or FDMA, or perhaps CDMA. So SDMA by itself in wireless power transmission is not sufficient. So this is our initial conclusions. We are still working on it. So this is the end of my brief presentation. Thank you.
Thank you very much. Our next presenter, Yuki Tanaka.
Thank you, Chairman. Can you hear me?
Yeah, can you share your camera or possible? Yeah.
Okay, just a moment.
Sure. Yeah, sure. Thanks.
Okay, thank you. Hello, everyone. I am Yuki Tanaka from Panasonic Corporation. I will talk about distributed microwave wireless power transfer with backscatter feedback. Please show next slide. Okay, thank you. First, I will talk about distributed I will explain the background of development of distributed MPT. Recently, numerous devices are communicating wirelessly in IoT and 5G fields. The microwave power transfer has been studied for powering those devices. There is no perfect solution. For example, method of transmitting a wide beam such as RFID system can reduce the size of transmitter and the receiver, but the efficiency is quite low. On the other hand, the narrow beam method that uses beamforming is high efficiency, but requires a large transmitting antenna. Furthermore, higher radio emission is harmful to the human body. Therefore, safety and highly efficient WPT is required. Our approach is distributed WPT. This is large distributed phased array antenna system. The antenna transmit power at the same frequency. The system has 10 to 1,000 transmitting antennas. And we use a closed loop system for phase optimization. In third slide, we can see a measurement result. At this time, frequency is synchronized and phase are optimized so that received power is maximized at a point. The measurement result is good agreement with simulation. With higher power is focused in the pre-configured point. You can see that the spot size is smaller than 1 wavelength. The maximum received power was 6.5 milliwatt. In conclusion, this study, we showed that the distributed MPT improves the received power by n times. N is number of transmitting antenna. And then we propose a simple and low power consumption feedback system using backscatter at the simulation and experiment. In the future, we will continue to research and implement even faster optimization algorithms and aim to supply power to multiple power receivers at the same time. That's all. Thank you.
Thank you very much. Our next presenter, Dean Matos. Matos? Diego Matos?
Hi. Can you hear me?
Yes, I can hear you. Go on.
Okay, thank you for the introduction. Can you move to the next slide, please? Okay, our work is based on ultra-wideband PAM backscatter modulator. The intention of this work was based on trying to reduce the energy waste and the battery dependency of these devices. And for that, we propose to use existing ambient waves to reduce the necessity of batteries and a dedicated transmitter to perform the modulation. So the method and the approach that we took was based on the 130 nanometers BCMOS backscatter modulator that has very low power consumption, and we characterized the device in a wide range of frequency. In the paper, we present from 100 megahertz to 6 gigahertz, and we show that the circuit is capable of performing PAM modulation in all of that frequencies. And then we use a low-cost software-defined radio to demodulate the modulated signals. So for that, we had several considerations. First, we did with multiple input power levels to see how low we could go, and also for different values of data rate. So we were able to demodulate signals with an input power range from -10 to -60 dBm, and with data rates from 5 to 50 kilobits per second. And we demonstrated that for different frequencies. And in future work proposal, we would like to try for more frequencies and try to use another SDR module to trying to work on the data rate value. Thank you.
Thanks, Diogo. Our next presenter, Ricardo Pereira. You can.
Yes. Hello.
Yes. Hi, Ricardo.
Thank you. So the title of my presentation is Focus Location Measurement of a Quasi-Optical Double Reflector System. And basically the aim of our work was to study wireless power transfer by using the Quasi-Optical framework. This is basically a modified version of optics, which takes into account the high divergence of the radiation, in this case microwaves. And so in this paper, we wanted to show the results we obtained of the experiment in order to verify the theoretical results we had studied previously. The overall goal is to reduce the spillover losses in wireless power transfer systems. In order to do that, the method was that we developed a system composed of two horn antennas that were 3D printed, and we used them, one for emitting radiation towards a reflector, and the other was used to measure the S21 parameter. We consider that we achieved the maximum, that we achieved the focus location when the maximum S21 was obtained. And so we swept a distance from 1.9 meters to 2.75, and the key results are exactly that. To conclude, we successfully measured the focus location, although it was slightly different from the theoretically expected by 5 centimeters. The next step is to experiment with the complete system, that is with 2 reflectors instead of just 1. And one major conclusion is that we identified a need to develop the solution for measuring the exact Gaussian beam in different positions so that we know exactly what is going on in our system. Thank you very much.
Thanks, Ricardo. Now we are Icaro Suarez, or Isaro Suarez. Yes, go on. Sorry.
Thank you very much. Good evening, everyone. So my work is about efficiency enhancement in mid-range RWPT systems by using green meta-surface lenses. Could you go to the next slide, please? Yeah, perfect. Our goal is to design the mid-range WPT system with enhanced efficiency. So here, the middle, because in this kind of systems, the efficiency is strongly deteriorated by the reduction of the coupling between receiver and transmitter. And it's mainly due to the distance between them and the misalignments. So our idea is to apply one technique that's already vastly used in optics, is the gradient refractive index metamaterials, in order to focus the magnetic field in a desired direction. So it could solve problems with misalignments, for example. So our idea, different from the conventional metasurfaces lenses, in which the unit cells are the same, distributed along the full structure. Here, each unit cell, it's changed by changing the capacitance. We can change the refractive index of each unit cell. So we can we define a gradient of this refractive index, and then based on this gradient, we can focus in one desired direction. So this is our method. We apply this technique, and all your unit cells have effective permittivity less than 0. And then we can turn the effective refractive index by changing the lambda capacitance. Based on this, we could get we did the same using the same structure with the conventional lens that we can find in literature. The efficiency was around 18%, and with our proposed lengths, this efficiency goes to 33%. So based on this, this is a technique already known in literature, but never applied before for metamaterials in our power transfer systems. Can increase the coupling and reduce the dispersed magnetic field between the transmitter and the receiver coils. And it can be also used to design controllable lenses in order to focus in a desired direction and reduce the misalignments and the losses between them, between transmitter and receiver. Thank you very much.
Thank you very much. Our next speaker, Francesca Binassi.
Yeah, it's me. Good evening. Thank you, Mr. Chairman, for this introduction, and welcome to all the colleagues. My name is Francesca Benassi. I'm a current PhD student at the University of Bologna, and today I'd like to summarize in 2 minutes my work titled Wireless Power Transfer in the Radiative Near Field through Resonant Bezel Beam Launchers at Millimeter Wave. This work has been carried out in collaboration with colleagues Dr. Barte Fuscaldo and Professor Alessandro Galli from the University of La Sapienza, Rome. So it's a co-author work. Next slide, please. So the goal of this work falls within a bigger framework of a national project called Wireless Power Transfer for wearable and implantable devices, which aims to design wearable systems, or better, wireless power transfer system for powering wearable devices, both wearable and implantable, using millimeter wave. In particular, this work is focused on the novel design of a radiative near field system working at 37.5 gigahertz and making use of bezel beam launchers at transmitting and receiving antennas. The use of these type of antennas have been chosen because of their high focusing capabilities, which is exploiting this kind of application. The methods we use and the approach we use to derive some results were first the characterization by full wave simulation of the antenna itself, and then through a numerical customized algorithm, we were able to establish a power budget of the antenna link, which for, let's say, common cases, or in a general way, it takes into account the full wave simulation of the both antennas, but with the customized algorithm, which exploits the electromagnetic theory, in particular the equivalence and the reciprocity theorem, we were able to make and establish overestimate the power budget by just simulating one antenna by full-wave simulation, thus reducing 1/2 the overall computational time. By this numerical algorithm, we were able to establish the received power in certain different conditions, in particular for different reference distance between the two launchers. So going from a minimum distance of 10 millimeter up to a maximum distance of 40 millimeter. With, as we can see from the table, the received power goes from 6.3 dBm down to -5.5 for the maximum distance, with an overall efficiency of the wireless link, which reaches the highest point of 21.35%. Last but not least, we were focused on the design of the rectangle, so we performed the optimization through the harmonic balance algorithm by using circuitous simulators, and we designed a halfway rectifier in order to maximize the ref to receive power conversion efficiency while maintaining the reduced number of components. As conclusion, this is the work I presented and tried to summarize in a 2 minutes speech. And as future goal, we are aiming to investigate new feeding techniques in order to extend the non-diffracting range, which is the range in which this vessel be maintained their non-diffractive behavior, which ideally can be extended up to infinitive, but due to the reduced dimension of the antenna is confined on a specific region called non-diffracting range. And in particular, we would like to target our application in order to be exploited within a more specified biomedical field. In particular, we would like to investigate the performance with different feeding techniques in the presence of biological tissues. Thank you very much for this attention.
Thank you very much. Our next presenter will be Shen Jiang.
Yes.
Yes, hi, Shen Jiang.
Hi. So hello everyone, this is Xin Jiang from Kyushu University, and our work is a design of a 3-layer stacked metasurface and its application to compact dual-band WPTC system. And next slide, please. So for the medical application, our goals, as shown in the top left, are trying to make the whole device compact enough to be implanted inside the human body, and also efficient enough at a longer distance for the robust wireless transmission, and also for the power supply and the information can be exchanged simultaneously for the body area network. So the way to estimate and optimize the permeability of the proposed metasurface is shown in the bottom left. Both real and imaginary parts of the permeability at the desired frequencies are near 0. But however, because of the refractive index on the higher band is near -1, so most of the wave beams are reflected, resulting in a huge decrease in the higher band. So in the as shown in the top right, and so in the nutshell, in the simulation part of the permeability of the proposed metasurface exhibits the negative and near 0 characteristics in the frequency range of the interest, which results in the improvement of the efficiency more than 10% when the WPT distance improves from 19 millimeter to 23 millimeter at the lower band. And also the metasurface is designed to be vertically to save the area of the whole system. Thank you.
Thanks, Shen. I think this is our last speaker, Mizuki Masa.
Yes.
Yes.
Thank you, Chairman. And I'm Mizuki Masa from Kyoto University, and I'm going to talk about this title. Please go to the next page. Thank you. As IoT technology becomes popular, the simultaneous wireless wireless information and power transfer, SWIFT, is more needed, and but the frequencies allocations for them are insufficient. So we aim to realize SWIFT at the same frequency using the OM mode orthogonality. OM means the orbital angular momentum, and it represents the angular momentum around the propagation axis. And so we studied which OM mode can get high power transmission efficiency and how much isolation can be realized. To study them, we investigated the power transmission efficiency, and the mode isolation was changed depending on the transmission distance d by simulation. And we got the result as I show in right upper figure. And in the result of power transmission efficiency, we got we can see that when we use the high mode number, then we got low efficiency, and we got up to about 7% of efficiency. And in the result of mode isolation, we can see that when we use the equal modes evenness for receiving OM mode to the transmitting OM mode, then we got low isolation, and we got up to about 60 dB. And then we got the conclusion mode 0 is suitable for WPT and other structure or way which can achieve higher power transmission efficiency is better. And modes evenness should not be the same for transmitting and receiving OM mode. And using the OM mode's orthogonality is suitable for suitable for SWIFT. That's all. Thank you.
Thank you very much all for your time and your great presentations. And now we open the time for Q&A. So yeah, I need to check questions.
There are no questions yet.
Okay. I think we have one question. Question for TS6, presentation 3 to Takanori. What do you mean by no polarization in your key results?
Yes, this is Takanori Mashiro. Thank you for the question. No polarization, it means that we use the longitudinal wave to transmit power. So there is no polarization, and it means even if we change the direction of the antenna for 90 degrees, it still can receive the same power level. We can change freely to the direction of the antenna. No polarization means these characteristics.
Okay. Thanks.
There's a question from Dr. Benassi, for Dr. Benassi. What is the depth of penetration for the 33.5 gigahertz for medical implants?
Oh, thank you for this very interesting question. Honestly, when working millimeter wave went for biomedical application, so for targeting biomedical application, it's still quite a challenge to define the actual penetration depth because of the biological tissues that are interposed. For the moment, we are investigating the performance, just not taking into consideration the biomedical tissues, but we are expecting to be able to achieve a penetration depth at least some centimeters. So we're aiming to reach for penetration depth that enables the powering of implantable devices which are placed not right after or underneath the skin, but in very close proximity of the skin. So not deeper implant by exploiting this kind of technology, and in particular these millimeter wave frequencies. But as I said, we are in the process of investigating these new feeding techniques in order to apply this technology to the more biomedical field.
Is there a reason you chose 33.5 gigahertz in terms of the attenuation versus distance through human tissue or anything like that?
No, we choose the resonant frequency of 37.5 gigahertz because the bezel beam antenna that we were using was, let's say, already predefined. So we wanted to exploit that because of their capability of focusing the beam. And in particular, this was something we were interested in, especially for avoiding the other tissue to be invested when misalignment occurs. So this bezel beam techniques is really exploited when you want to focus the beam in a certain specific region. So this was seen from our point of view as an added value more than a drawback. And in particular, this frequency was a good compromise and a good trade-off between bezel beam properties in terms of beam properties, so confinement ratio and non-diffractive range, and also a good trade-off between bezel beam properties and resonant condition for the antenna that we designed.
Thank you. Other questions for the same speaker? Do you have issues with scattering at these frequencies?
Actually,
that, to be honest, correct?
Yeah, one of the characteristics of this type of antenna is the fact they have this non-diffracting behavior. So although they may experience some scattering during their propagation, they kind of have a capability of regenerating throughout the process of being radiated towards a certain distance. So in that case, we didn't experience it for the moment because we didn't take into account any interposed body, any interposed tissues for the moment, but we are expecting if faced to overcome in a better way by just exploiting this type of technology.
And the follow-up question, what power transfer efficiency do you expect? And maybe you could elaborate on that efficiency of through free space as well as through the tissue.
Yeah, of course, the free space attenuation, this frequency is really an important value to be, an important thing to be considered when talking about efficiency in wireless power transfer system for millimeter waves. In this case, we are expecting efficiency of, let's say it's hard to define because it depends on the distance we want to achieve, but as referring to the table, we were able to reach for a distance of 10 millimeter between the launcher, about 21% radiation efficiency, which decreases with the distance when the distance increases. So for a target, we were expecting some percentage of efficiency for a target distance of about 40-45 millimeter distance between the antennas. Of course, when dealing with biological tissues interposed, we can expect a decreasing of this efficiency. That's why we are thinking of different feeding techniques in order to exploit other advantages of these type of antennas, which can be more suitable for this kind of application, especially in the presence of biological tissues.
But as far as raw numbers for the efficiency?
Well, as far as by experience, the efficiency of about 2-3% for an average distance of about 20-25 centimeters between the two launchers. For this dimension, this frequency, I think is quite achievable.
Thank you.
You're welcome.
I have a question. So for slide 5, Yuki Tanaka, I see that you have used the backscatter communication. Can you comment on the why did you use that, and maybe the differences between that and Bluetooth BLE communications? Like how much throughput do you need for your communication, and maybe also comment on your overall system efficiency?
Thank you for questions, Hochema. We use backscatter modulation. This is very low power, very low power for transmitting the signal proportional to receiving power. Backscattering signal is proportional to receiving power, and we use the RSSI of the backscatter signal.
So what is, why did you use that and didn't use, for example, BLE, Bluetooth, low energy communications?
BLE is radio communication. For example, BLE is very high need, high current, high power consumption.
Okay.
So we use we not use BLE now, but in the future we will use BLE or other radio communication method for phase optimization.
Yes. So can you elaborate on your phase optimization algorithm, or what do you mean by that?
Phase optimization. We use phase optimization method in, of simple. We use now hill climbing method, simple optimization method. Hill climbing method was used in this time, but for multiple receiving optimization for multiple receiving target, more complex algorithm is needed. It is our future work.
Okay. Does the phase optimization give you kind of new, like more throughput, or it is just for making the system functional?
I'm sorry. Your question is how much is throughput of backscatter signal?
Yes. Yeah.
In this work, this is no radio communication. There is no signal or information. We use only RSSI signal, and it is no throughput. This is no throughput. Throughput is 0.
Okay.
I think.
Can I ask a question of Mr. Tanaka? That's all right.
Thank you. Okay.
Sure. So you're proposing the system with the multiple transmitters, and as you note, it's not a communication system. And the communication system with multiple transmitters, we may not be quite so concerned about the spacing between the transmitters, as long as we can focus the information where we need it. But with power beaming, do you have to take into account the spacing of these transmitters carefully due to issues like grating lobes and things like that?
There is many grating lobe, but grating lobe is very flat by distributed antenna placed broadly, and the problem of grating lobe is quite low.
But there will be some angles where you'll be transmitting power via grating lobes, as well as the place that you're trying to focus the power to. That'll impact the efficiency effectively, right? To some extent.
Energy by grating lobe is low. Energy by grating lobe is high than it as a narrow beam method.
All right.
Okay, thank you.
There's some additional questions here.
I think the slide presentation 3, correct?
Yes. Would you like to address
No,
this?
let's go on. No, go on. That's okay.
Go ahead.
Okay. I think I did a theoretical study of WPT to electric and magnetic dipoles, and I found that geometric parameter, which may be useful for characterizing your resonant receivers, if the dipole receiver has a characteristic length scale of D. I think Robert Moffat found the power transfer to the receiver is proportional to the volume, where Q is the quality factor of the receiver resonator. So I think the question is about the Q, the quality factor of the receiver resonator. What value do you have? I think the question is to Takanori Washiro. Slide 3, presentation 3, Takanori. Like what value of Q do you have in your receiver resonator? And does it relate to, how does it relate to the power transfer to the receiver? We cannot hear you. I think you are muted.
Sorry, I couldn't hear you very clearly, so please.
So the question is about the quality factor of the receiver resonator that you have.
Quality factor.
Yes.
We didn't measure the quality factor directly, but the transmission efficiency is about 80% or so from between the antenna to antenna.
Okay, but this doesn't. Okay, yeah. Thank you very much.
There's another question. This one is for the final speaker. What was the reason orbital angular momentum, or OAM, is considered for wireless power transfer in the first place? He says OAM would provide much greater bandwidth density for communication systems. It's interesting that OAM is adopted for wireless power transfer. I wonder if Miss Mizuki Masi could answer this.
Yes. Thank you for this question. And first, the reason for why we chose to use the OAM mode. First, we can use few frequency, so we can save the use of frequency.
I wonder, is this because you were trying to isolate a communication signal and a power beaming signal from each other?
Yes.
Motivation, okay. So for future wireless communications, you're trying to power a wireless device and communicate with it at the same time, and you'd like to have a separate receiver for the communications, but occupy the same bandwidth.
Yes, absolutely.
Okay.
Is this useful for near field or far field kind of wireless power transfer? What do you recommend?
From the result we got in the study, maybe we can get high power both high power transmission efficiency and high model isolation. The transmission distance D is large and far field. So maybe it is better to use this system at the far field.
I'm not sure, right? Orbital angular momentum is a near field effect, right? So this would be useful, I would think, for communications in the near field or Fresnel zone, or for power transfer in the near field of Fresnel zone, right? But as you go to the far field, orbital angular momentum is essentially a near field effect from everything I've seen.
Yes. From the result, we got high modularization and high power transmission efficiency at the far field, but it is near the Fresnel zone. So not so large distance is better.
Any further questions?
I guess I have another question, perhaps, for the speaker, Ms. Benassi from the University of Bologna.
Yes, I'm here.
Thanks. So we've heard something about Bessel beams, and here you're operating in the near field with Bessel beam. In power beaming, for the benefit of the audience, in power beaming, we've typically thought of Gaussian beams and truncated Gaussian beams as optimal, right? At what point do you get close enough in the near field where this Bessel beam becomes better than the Gaussian beam?
Okay. Let's say that for this application, we didn't really investigate the effect of the Gaussian beam in this kind of application. So we pretty much stick with the Bessel beam design, which, as I said, was since it was a co-author work, the colleagues from La Sapienza were dedicated to the design of antenna. And in particular, we exploited that antenna that was already designed by just working in a different frequency in order to match the efficiency and the matching condition. In that case, for the, we didn't really investigate, but it's actually interesting to evaluate what are the difference if exploiting Bessel beams or a Gaussian beam for the same reference distance. So at the moment, we didn't really experience any, we didn't really perform any analysis to see how close we need to get in order to see which one is the best between the two. But that's quite a nice suggestion that we'd like to investigate.
The beam collection efficiency, basically, versus distance for each approach would be very informative.
Thank you for the suggestion. Really interesting. We will take into consideration. Thank you very much.
So we have another question. Could the person addressing this question elaborate a little bit more? Okay.
Oh, I guess from attendee, they won't be able to talk, and I need to do something here. So that's Dr. Mackin.
Okay.
So Dr. Mackin, you can talk.
Yes, yes. Thank you. Thank you so much. Oh, so much control you have. My goodness. Omnipotent. So I was just commenting to your question, Dr. Rodenbeck. Basically, you know, with these Bessel beams, a few wavelengths from the source is where basically the singularities start hitting. And, you know, all that collimations goes out of the window because you have all kinds of diffraction patterns that set in. And we do that all the time in acoustics, you know, where you have a flat planar source and you're trying to collimate the beam. And you have a near field, which is a Bessel function, basically, at that transition zone between far field and near field, but close to the source, a few wavelengths at gigahertz.
I think I understand the application here. This is a good means for very near field power transfer if you have an electrically large aperture.
Yes.
You might at millimeter wave.
Yes, yes. Thank you. Thank you very much. You can mute me if you want.
Yeah, just a quick comment. I mean, as I try to summarize in the 2 minutes, but of course it's it's a very short time to summarize this work. We were confined between dimension constraints and efficiency in terms of vessel beam generation. So in that case, we wanted to achieve the minimum distance while at the same time reaching for a good vessel beam profile according to the J0 profile. And so that's the reason why we achieved for this operating distance. But of course, if you're taking into account larger aperture of antennas, so getting, of course, bigger than these 44 millimeter of diameter of our antenna, you can achieve further distances in terms of non-diffracting range. So of course, you can actually improve the distances which can power the one device. So our application was just confined, and we give ourselves some constraints into the design for the antenna itself. And thus we had some effects in the overall performance, but for the moment, we are pretty happy with the results. So is the first work in this field for our group, and we would like to start from this and improve the results. Thank you very much.
So maybe a question for the first speaker, Mr. Fazzini.
Yes, let me help.
So you talked a little bit about range selective focusing with a frequency diverse array.
Yep.
Could you comment on how this might scale to an array that will transmit in 2 dimensions and scale to large sizes?
Yeah, the concept of, oh, sorry.
The frequency diverse.
Okay, yeah. The frequency diverse is a technique for which we use different signal for different radiating elements, for which we radiate a frequency that for one element of the array that is slightly different from the frequency transmitted by the neighbors, of course. And this planar array is used in our project to investigating the 3D properties of the frequency diverse array. And using the frequency diversity, the main characteristic that we get from this scheme is the ranging capability, that is the capability to provide energy not only in a certain direction from the source as phased array or time modulated arrays or other arrays, but is the capability to provide energy at certain distance from the source, and this can be achievable only with the frequency diverse array scheme. And in literature, unfortunately, the research on frequency diverse array until now is regarded to linear arrays, so array that are disposed along one axis of the Cartesian reference system. In this case, we want to, and of course, the frequency diverse array capability is investigated on the radar cross section, so on the plane that containing this alignment of elements. In our case, we disposed a planar array that is a matrix array for which we implemented the frequency diversity along the several columns of this matrix array, and we investigating the 3D properties. So on the beamforming characteristic in all the phi planes that we are interested on.
Can I ask a question, maybe a higher level question?
Yeah,
so
of course.
You're talking about range selective power focusing,
yeah.
Correct. So are there, would this effect be something like with radar with ambiguous ranges, so that it's not just focusing at one range, but at some periodicity of ranges. And what would be what are the trade-offs in architecting your waveform to keep the range from being ambiguous?
Yeah, of course, yes, thanks you for the question. This is a very good question because at the moment we need to differentiate between two different applications because at the moment we are investigating on wireless power transfer application, not a radar application that involves a different, we can say, frequency increment parameter. But in order to not be ambiguous, we need to perform. We need to state that we have a periodicity in time and a periodicity in space of the radiation. And this periodicity in space is given by the fraction between c, that is the velocity of the light, and the delta f that we have in our, the delta f, it's the increment of frequency that we have between the different waveforms. And so in order to not be ambiguous, we need to we can say restore a waveform period that is less than the period of the inverse period of the frequency increment. So we can, for example, brush the space for specific interval, and then we can tune off our pulse, we can say, and periodically repeat this type of structure in order to not have ambiguous, we can say, ambiguous range selection spots.
Okay. Okay, so there's ultimately a trade-off between the range and the range ambiguity, right?
Yeah.
So you can't maybe go, if you want it to be unambiguous, it has to be closer.
Yeah, of course.
For given frequencies. Okay. Yeah. I think I understand. I'll have to wait for your full paper.
Yeah, sure. Yeah, we'll wait all for your paper. Thanks, Enrico and Chris.
Thank you very much.
Yeah.
Can I add maybe to talk to some of the other speakers that we haven't had questions for? Would it be all right if I ask a question to Mr. Morrow right now?
Is this the last question?
Oh, yeah. Can we do one more question?
Okay, sure.
So, yeah, Mr. Morrow, you're talking about powering a drone in flight at 28 gigahertz. And I think from our keynote speaker, he was talking about the advantages that might come to using lasers for powering drones. How do you think laser and 28 gigahertz compare for powering drones, the pros and the cons of one versus the other?
We choose 28 gigahertz because it might be most efficient for a drone to wirelessly power beaming. As we assuming few assumptions such as the transmitter antenna size and the receiver antenna size, and the transmission distance. As a result of few assumptions, we clarified the 28 gigahertz microwave beaming is the most efficient. So we will not use the laser beam forming because it might be the higher frequency than 28 gigahertz, and maybe it will cause the lower efficiency than 28 gigahertz.
All right.
Okay. Thank you all very much for your time, and thanks to all our speakers for this great presentations. And thank you, Chris, for co-chairing this session. And I'd like to remind all of our audience that we should have still 3 sessions tomorrow, and hope you can attend these. And with that, we can conclude, and thanks again. Okay, bye.
Thank you. Thank you for all
very much.
speakers.
Bye. Oh yeah, thanks Paul as well. You are still here. Yeah, thank you Paul very much for your speech. It was great and we like it all. Thanks.
Great session. Thank you.
And great job chairing your session. Thank you, Mohammed. Thank you, Chris.
Thank
and
you.
thanks all the speakers and audience staying so long. Okay.
Thank you very much.
All right. So see you in the next session.
Thank you all.
Thank you all. Bye.
Bye.